Welcome to Three Devs and a Maybe. Now introducing your show hosts, Michael Budd, Fraser Hart, Lewis Gaines, and Ed Mann.
Hello and welcome to another episode of Three Devs and a Maybe. My name's Ed Mann, and today we're joined yet again by Bruce Momjian. How you doing, Bruce?
Hey, very good. Good to be with you again.
Oh, thanks again for taking the time to come on the show. I really appreciate it. It was so interesting. The last episode we did with you talking about like unlocking the query planner and looking more into like the relational database kernels. Because I do think it's one of those things where, you know, you take for granted kind of this black box that just works for you. And like when we uncovered the query planner stuff and like looking into how it actually works, I thought for me it was definitely interesting and kind of fulfilling and understanding that was great. And I think for the audience it was good too. And I think today it'd be really interesting actually, if you don't mind, maybe us going more into like the concurrency and locking and really kind of how a database, like a relational database, handles multiple actions occurring at the same time. Because I do think something like that is, again, it's like we take it for granted. We kind of just assume, yeah, no, the database will handle that. And it's something you should really take into consideration, especially as, you know, it's not a free lunch. You know, there are certain bits that are very, you know, once you start doing more and getting more involved, you know, you do really want to understand like kind of space and performance characteristics of it. So I thought maybe the first question would be great to ask is actually, what is concurrency?
Yeah, I agree with you on understanding how it works. You know, you look at a lot of things that people make or build, and you look, gee whiz, how does that work? You know, how does an engine work, or you know, how does a TV work, or how does streaming video work? You know, these are all kind of really interesting questions, and you know, I think there's a natural curiosity that you want to understand how something works, and also I think you're a better user or more effective if you understand some of the background of how stuff works inside. And I think concurrency is part of that. Frankly, I often give talks about, you know, why use a database. You know, you start from really basics, and you say, well, why should I use a relational database? Why would I not use a non-relational database? Why wouldn't I use a flat file or some kind of ISAM setup, or, you know, some homegrown storage system? And a lot of that really revolves around the kind of services that the relational system provides. And I think one of the most invisible services is concurrency. You know, when you're sitting in an SQL prompt and you're sort of typing a query in and hitting enter, getting the result back, it's really not obvious that the system has done anything for you in terms of concurrency. You gave it a request and it gave you the result back. What's the big deal? But in fact, when you start to understand that there are perhaps dozens or hundreds, potentially thousands of people who are doing the exact same type of query at the exact same time, it is somewhat magical that they're all able to return accurate and consistent results without really any user interaction at all. It just kind of happens. And if you've ever tried to do a database that isn't relational, or a case where you're trying to do something with flat files in concurrency, which is really, you know, really horrendous in terms of what can be done, you know, you start to realize that, oh, gee, the solution that works for one user just does not work when concurrency gets involved. And frankly, when I start to look at new projects, or as a consultant, when I used to work on projects, you know, I used to, in the back of my mind, say, you know, if this is a single user application, and there are a good number of those out there, you know, the complexity is X. But if it's a multi-user application, you know, the complexity is 3 or 4X. Just adding the need to have multiple people in that application at the same time really changes a lot of the behavior of and adds a huge amount of complexity that just didn't exist before. So in a way, you know, concurrency for databases is successful when it's invisible. It's the kind of thing where, when they go up to sing the national anthem, you just expect them to do it perfectly every time. And if they don't, then you notice it. Again, it's sort of like if you make the job look easy, then you succeeded. And if you make it look hard, you haven't. And there actually are some databases that do make concurrency look hard. And they do get sort of a ding when you compare them to databases like Postgres, which make concurrency look very easy, and everyone's like, oh gee, it doesn't have to be kind of hard. It can actually be something that I almost never have to think about. But of course, as database internals people, we're thinking about this all the time.
Well, I think that's really interesting because it really does then kind of mirror the kind of query planner discussion we spoke about last time, where, you kind of take for granted, and it's like a good database obviously is then hiding this.
Yeah, you're right. It's exactly the same thing. I mean, the best query plan optimizer is one that you never know about, or you never have to understand. You never have to look at an explain plan or optimize, because it does everything perfectly all the time. And this is the similar kind of thing. The goal of the database is to get out of the way and allow people to write very simple requests that can be happening, dozens of times simultaneously, or hundreds or thousands of times simultaneously, and to return results that are consistent no matter what else is going on in the database, whether 20 people are updating and 20 people are reading at the same time, or 2,000 are doing the same. That is supposed to happen in a way that nobody really sees the effects of anyone else doing anything. The results are always fast. The results are always accurate. Any changes that are being made to the database, are sort of papered over, and you always get a consistent result. And that's really the goal of concurrency, is that you want to provide consistent results to users with a minimal amount of overhead or blocking or slowness related to other activity that's happening on the system. When you think back, 30, say 40 years, prior to maybe the 70s, a lot of the operating systems, or certainly the 50s, were single user. Right, and the goal of the newer operating systems, Linux and Unix are just some examples of multi-user operating systems. And the goal of a multi-user operating system was to allow multiple people to use the hardware at the same time in a transparent way, so each user really felt they were the only user on the system. And that's exactly what happens in databases, where your goal is to present something where each user feels they are the only person on the database. The difference is that in an operating system, you're basically arbitrating use of hardware and memory, particularly CPU, among these multiple people, giving them time slices of CPU, giving them some segments of memory. In a database, there's even a tighter commingling of users, because you have some users who may be updating rows that other people are reading. They're updating different rows and other people are reading other rows, and there's indexes involved and joins and so forth. And concurrency is I would say even more intertangled in a database sometimes than it is in an operating system.
Yeah, because I was going to say, the dream then is to be able to use, obviously in the case of, say, a database, is to be able to use it. Everyone's using it. Everyone's updating. Everyone's inserting. Everyone's, reading, and they're all getting the latest and greatest, and there's no problems. But obviously, you say it's not a free lunch, and there are going to, the issue is, say, if I'm updating something that someone else is trying to read, or they're updating something and I'm trying to update something at the same time, it's the exact same thing. What wins out? I'm just wondering, what other, before kind of, I know obviously we're going to go on to what Postgres uses, but before that, the other ways of solving this are through locking and things like that. I'm just wondering, what's your experience with those and the pros and cons of such an approach?
Yeah, I would love to say that, I was a genius in this area, from when I was in my 20s, but, or my 30s, but I definitely wasn't. A lot of a lot of the learning I've done is looking at how Postgres has come upon a lot of these challenges and a lot of the problems that you don't normally think of, as a user of a database. And I was an application programmer for 12 years in the 90s, and I didn't really think a lot of times about some of the complexities of what we had to do. But at that time, I was an Ingress user and an Informix user, and I remember, writing database applications, and normal applications seemed to run fine. You would get the occasional case where somebody kind of had left a screen open and the rest of the staff were kind of stymied. Like they had left something open or a particular record, and I would get a call. At that point, I was a consultant for law firms, and there was a bunch of law firms I serviced. And I would get a call, and they'd say, we can't seem to access this one record. Can you find out what has happened? And I think I don't remember how I did it, but somehow I would kind of dig around, and I would say, oh, I think it's this user. Can you go to their screen and see what they're doing? And we kind of papered it over, and there was sort of an assumption within the organization that again, as I said, the best concurrency is the invisible one, and this was not invisible. There was some sense that if somebody was on a particular record or was making a particular change to a customer, if somebody else tried to do the same thing, they would, or even if somebody, this was interesting, if somebody even tried to look at the record, they would kind of get stuck, and they would kind of hang, and they would get a chance to exit, but they were kind of stuck waiting. So there was a little bit of sort of lack of pipelining where you had to get people kind of going. And normally it worked fine because most people were changing a relative small percentage of the database, and the odds that somebody else was going to come over was going to be pretty rare. But me as a database administrator, I often had to make massive changes to the database. So I had to change, maybe thousands of records, or maybe every customer I had to do something to. And in those cases, anytime I did anything big, I kind of knew I didn't want to do that during the day. These were law firms, so it was kind of easy. It was, it was before the web really became, the thing where everyone stored their data. So everyone kind of went home at 6 o'clock. And in fact, I used to, for practical purposes, I had a very unusual work schedule. So I would often work from, say, 7 p.m. to 10 p.m., making data changes because I knew nobody was in the system. And then I would, sometimes that might go to 11 or 11:30, and then I might get up later the next morning. So my day even practically ended up being shifted, maybe 3 or 4 hours later, because I always needed that window at the end of the day. Because if I had to do a massive change, I knew I couldn't during the day. Even reporting was something that often had to be done off hours. So you had to do, kind of large reports. You had trouble running those during the day because they would often interfere with operations that were going on. Now you get with small reports, but there were certain reports that are known to be sort of hogs, and you would run those during off hours. I remember. Often, if I had to do a massive update on something, this was like sort of trial and error. If you did a massive update on something, you had to run it at night. And I remember running it for 45 minutes or an hour, and then getting an out of locks message, right? And I was like, oh my goodness, how am I going to do this? I'm getting this out of locks message, and I'm not even sure if I solved it that day. I might have had to call my boss the next morning and say, I don't know how to make this change. I'm getting these out of locks messages. What I would do, and he said, "Okay, well, the way you need to do it is you need to look at the sequence number of the table, and then you have to do it in chunks. So you have to do 0 to 1,000,000 in a query, and then make sure you get this right. So if make sure you don't forget the boundary. So if it's everything less than 1,000,000, you have to make it equal to or greater than 1,000,000 in your second one, but then less than 2,000,000. right? And then 2 million equals 2 million or more, but less than 3 million. And then you had to basically do these in stages at night, because obviously you didn't, you couldn't do it during the day because it would cause all sorts of havoc. And I remember, you sort of start the job and it's going to take 45 minutes, and you're like, well, what am I going to do for the next 45 minutes? I guess I would watch TV, or I don't know what I did, to read a book, because you're just sitting staring at the screen. At that time, you were dialed in on a modem and you were running it, but there was nothing you could do. You couldn't monitor it. You certainly didn't want to touch the database because it was doing this massive operation, and anything else might interfere with it. So you made sure nobody was running any reports. You didn't do anything extra. You just sort of let it go. And hopefully you got through that job. So I would say, concurrency in some of the databases from the 90s was, it required a little more thought on the part of the users, but the administrators really had to understand what was going on and had to do some pretty odd workarounds to make it work.
That is insane, yeah. And I think it's funny that you mentioned, because obviously, for day-to-day usage from people, they wouldn't see these problems. They'd be touching a very small percentage of the database. But as you say, like people like you, database administrators, touching a large set of, the actual database, you're going to hit these problems with things such as locks and stuff.
Yeah, I remember one customer, and I got to know these customers very well, and I would often be on site, and then sometimes I was working from home and sometimes from the office, because obviously the hours were just crazy. They weren't crazy long, they were just unusual. Every day had a different need for when you should be on the system. But I remember, they were all kind of in cubicles, and, you would just get this random, blurb from one of the cubicles, who's in client, ABC, and 3 cubicles down would say, I'm in there, I'll be out in 20 seconds. And then, the other person was able to get in. So they kind of did their own locking in a way, sort of advisory locking, say, hey, I'm over here and I'll be out soon. And reports were often a bigger problem, because you had reports would often go through all the customers. So I remember what they used to do is they run the reports during lunchtime. So there was one customer I remember would send out like a message to the staff, and they would say, please take your lunch between 12 and 1. We need to run a report for the end of month or something. And you would kind of make sure, people were out, not only for the locking concurrency problem, but I think also performance was going to suffer when we run this massive report. And we knew if we ran it with no one in there, we would get through in an hour. And if not, we wouldn't. So it was, they made do, and it worked, but it was certainly less than ideal.
I think that's less than ideal for sure. But I do love the fact that they did, their own advisory locking and kind of got around it that way.
Yeah, because the users are very smart. I remember they used to, it was their job to use this application, so they knew pretty quickly when something didn't work. And they would either ask for advice from me or from the software vendor to try and figure out how they could, get around whatever roadblock was being, put in their way. It was kind of funny.
So you got from this then, where you're locking and you have to kind of orchestrate who's in that record and how do I run this report? I've got to run it, at a certain time when it's very quiet. How do we get from that then to where we are now, really? Like how Postgres runs now? I mean, as you say, like when we're looking at it, typical use cases, we kind of take for granted now the fact that we get concurrency and we get to handle this thing without ever having to really worry. So what does actually Postgres then use?
So. Obviously, this behavior is sort of this behavior we're describing from the 90s is pretty intuitive. So, the idea is you have a table with 100 rows, so therefore, you have 100 records stored in the database, and if somebody wants to modify one, well we got to stop anyone else from modifying it, and we also have to stop anyone else from reading it, because as we're modifying it, we don't know if that transaction is going to commit or not. So we don't want to show somebody data that's never been committed. So there's the intuitive way to do this kind of database is to have a one-to-one mapping. So you have 100 records and you have 100 rows stored in the database. But that worked when you were working on batch systems where you could sort of feed in one report at a time, right? That works really well because you don't have any concurrency. You're making optimal use of the hardware. But that really doesn't work well in a dynamic business because different people need information at different times, and you really can't. Although batch-oriented systems may be very efficient in terms of reducing locking problems or reducing this type of problem, I can't really wait in a queue to find out, what the balance is for a customer when they're on the phone, or they've sent me an email. I can't really sit behind, 20 different jobs to kind of, get through this. And there are some systems still today that take a batch-oriented approach. To concurrency, and they allow one person at a time, and that obviously reduces the locking, but it obviously also reduces the usefulness of the information because the information is not accessible. So about I guess in the 70s, I'm going back quite a bit, but in the 80s, they started to do research on how people might make better use of getting the data out of a system where you've got multiple people kind of in there at the same time. And the idea that's really kind of came up and has grown in popularity for several decades now is something called multi-version concurrency control, which is what Postgres supports. And it's kind of a fancy name and it's kind of a mouthful of words, but if you kind of break down the wording of what it's saying, it's basically saying that research has determined that the one-to-one mapping of the number of rows in a table to actual storage in the system is really not optimal. That when you have 100 rows logically in a table, if you limit yourself to 100 physical rows stored in the database, you're always going to have concurrency problems. I mean, that's just by definition. There's no way we can have somebody update a row and also supply read queries with some data because that data is going to be in flux. It can't be really read until it's committed and so forth. And there's all sorts of ways databases used to get around them. They used to allow something called dirty reads, which sounds terrible, but effectively would allow you to read data that hadn't been committed yet, and that may never be committed. It might be aborted later. So you'd have to run reports that potentially return data that wasn't accurate. And again, similar to the way that people used to work around the concurrency of locking for a record, they would somehow work around this dirty read problem, and maybe they'd hand the customer, the user, the report and say, "We think this is accurate," but if you really need the right numbers, I'll give them to you tomorrow. And sometimes that was sufficient. They weren't looking for. But that doesn't work if you're trying to balance the end of quarter or the end of month. Those numbers have to be accurate. So the way that researchers decide to solve this, they said, instead of overwriting a row when it's updated, let's make a new row. And let's keep a copy of the old row around for a while, so we can answer queries that don't need to see the new row. So what you effectively have, if you have a table with 100 logical rows, you may have 105 rows physically in the table. If 5 of those rows are currently being updated, or if 5 of those rows have recently been updated, and there are transactions that may potentially want to see those older versions of the row. So if you think of your table as 100 rows, it may be 95 static rows, which have 1 copy, and you may have 5 rows which have 2 copies in the same table, right? I know that sounds really odd, and it sounds like something you wouldn't want to do, but because of the research that was done academically and because of the very successful implementations that have been done, it's now clear that having extra copies of the rows for a brief time that you may need to keep those old versions really gets around a lot of the problems that I've outlined previous in this interview, that you got, problems with locking and problems with concurrency and people sort of being stuck, and even read-only reports actually having trouble because they can't get access to some rows that are concurrently being updated. By keeping those old versions around, you are able to actually provide much better concurrency and provide accurate answers in almost every situation. You still have some locking, but those locking situations are much more limited now.
Yeah, because it's the whole mantra that MVCC has, which is, readers never block writers and writers never block readers. And it does just sound like the golden ticket, doesn't it? Sounds like this is exactly what we want. And it's actually used in other things like closures, software transactional memory stuff, MVCC. So, I mean, coming out of the research stuff and then now being implemented into things like Postgres, am I right in thinking that it's in other databases as well? This is obviously now the de facto way of handling concurrency.
Yes, and I would almost say, certainly for relational systems, and even I would almost guess for non-relational, this is really the gold standard. This is where you want to be. And some of the databases have transitioned to that. Some of them are in the process of transitioning, however difficultly. Some of them may never make the transition, and maybe for performance reasons too. But Oracle has had it for many, many years. Microsoft SQL has it, but it's disabled by default, which I think tells me that they were originally a non-MVCC system, and there is quite a bit of re-architecture necessary to implement MVCC, and they may have decided that was not a direction they wanted to go. And similar, DB2 has kind of a partial implementation. I can go into the details of why it's partial, but it doesn't have the full spectrum of MVCC capabilities. My InnoDB, which is part of MySQL, has it, Informix has it, and Firebird has it. So it is sort of the golden ticket. It does sound really cool. It is hard to architect into an existing relational system. There is overhead involved. There is behavioral changes that potentially could happen. And it does take a lot of engineering to do this, and some systems may have been architected so well that they've sort of gotten around this in some other way, and they don't need to go MVCC. But certainly it's sort of considered to be the way to go. I think in the old days, maybe when you had very little storage and CPU was at a premium, maybe this would have been too much overhead. But at this point in the game, it's hard to imagine any downsides to really having it as an option.
Yeah, that's it now. Exactly. Like space and storage is cheap. It's all about getting it, concurrency right. And so with like the MVC, so you've got this idea of the MCC, pattern kind of thing. I would say like it's an idea, and obviously the idea needs to be implemented. And you've explained how MVCC works from a high level. I'm just wondering, like, how did Postgres come about to actually kind of decide on how it wanted to implement MVCC? Because I'm right in thinking that they all haven't decided on one true way of implementing it, and there's pros and cons of different ways.
Yeah, it is kind of interesting. Postgres originally did not have full MVCC. It was kind of implemented in the first maybe 2 or 3 years. It kind of solidified. It had some MVCC, but it wasn't full fledged. And by probably 1999 or 2000, it had been sort of fully structured and implemented in Postgres. But you're right. The idea of how to do it is pretty clear. You keep an old copy of the row around somewhere. And once you do that, you have to have some kind of tag on each row, because when you had 100 rows logically and you had 100 rows physically, it was very clear which, row 1 was row 1, right? There was only one version of it. It was there in the table. We didn't have to do anything fancy, right? Now, given my example just a minute ago, you've got 100 rows. As I said, 95 are static, right? And 5 of these rows now have 2 versions. So you're going to have to identify these 2 versions in some way, right? So is it version 1, version 2? Is it, version based on a time and a date? How do you identify, because you now have two copies of row 7, let's say, right? How do you figure out which one is which? You've got to tag it somehow. You've got to store them somehow. You probably don't want 2 copies of version of row 7 around forever, right? Because that's that old row. Once that new row commits, so let's say we have an old version, a new version, just to make it simple, eventually that new version is going to commit, or if it does commit, then you have 2 versions. You have an old and a new, and eventually you're going to want to get rid of the old version, because if you don't ever get rid of the old versions, you end up with a lot of clogged, your table becomes very large for really no purpose. So the ideal case is you tag these versions in some way, and you keep around as many versions as you need to supply read-only queries. So again, somebody who's running a financial report may need to see a copy of the old row, and therefore we need to keep that around. Now, once all these old transactions finish, and logically nobody should be able to see the old row, we should be able to remove that old row silently. The user doesn't need to do anything; it should just go away. And then we can reuse that space for future updates or future copies of old rows or whatever. Different databases implement it differently, but that's fundamentally what happens. You keep around 1 or more copies of previous rows, and then you sort of silently clean those up going forward. And again, if you do it well, then nobody really needs to know what's going on, either at the database, either at the user level or at the administrator level, and everyone's happy, and Postgres does its magic.
So obviously that example you gave there. So someone's running a financial report, and then while they're running that financial report, someone does an update. Obviously, in the past, either that update would be like can't happen, or the select with dirty reads or something, it may be improper, incorrect, or something like that. That may fail. Now, what happens though is both work, but then the select query is using an older representation of, say, that row that's been updated. Obviously, I mean, people never really think that. I think people assume, they just get the updated version there. Like, I guess there's always interesting little kind of problems to say, like, maybe if I'm updating a row in one transaction, I'm updating a row in another transaction, I then commit one of these transactions and the other one. What actually happens in that case? Like, kind of there is still going to be conflict resolution, I'm guessing, required in these kind of cases.
Yeah, you still have to. Somebody's got to make a decision at some point about how to handle that case. And Postgres pretty clearly makes the decision for the user. And surprisingly, we don't really get challenged on that. So, for example, if you're running a financial report, and that's obviously the area I'm most familiar with, having written so many of them. If you're running a financial report, you want a consistent view of that database at the time the financial report started. So, I mean, the classic case from database academic literature is a case where you transfer $100 from one account to another account. So, let's suppose my bank account and my son's bank account are at the same bank, and I get online and I transfer $100 from from my account to his account. And let's suppose at the same time somebody runs a financial report and they want to know how much money's in the bank, what's the total assets of the bank. Well, there's 2 anomalies that can happen there, neither of which are ideal. One case would be that the $100 leaves my account but is not identified as being in his account. So $100 kind of disappears, right? So if you gave somebody accurate view of the database at the moment they're reading each row, okay? So if you basically said, I want to see the most recent copy of each row as I touch each row, okay, you potentially have the problem where either you lose $100 because you see the money has left my account, but you don't see it going into his account, or you see it twice where it's in my account and then you see it in his account later, and all of a sudden you're misreporting how much money's in the bank. Either you're reporting $100 too much or $100 that's not enough, and both of them are not good. So what Postgres basically says, it says, okay, when you start a query, or potentially even if you start a transaction, and we can talk about the details of that, we guarantee to give you a consistent snapshot or consistent view of the data. So effectively, in that particular case that I've just outlined with the $100, when you start summing that table, we sort of put a line in the sand and we say that query has started, it has touched the first row of that table, and then we guarantee that user will see a consistent view of that table as it existed when they touched the first row. And the only way that's possible is MVCC, and the only way that's possible is to keep around old copies of what my record looked like before the $100 went out of my account, and another copy of my son's record before the $100 went into his account. So we effectively tag each row of Postgres with a transaction ID that represents when the row was created, and a transaction ID when the row was expired, perhaps deleted, perhaps updated. And because we do that, when we scan through a table, we go through a very complicated set of visibility checks, so that even if there's, as again, going back to our example before, if there's two versions of row 7, we make sure that when your query hits row 7, it gets the version of the row that matches the snapshot, or that matches the state of the table at the time you started scanning that table with row 1. So that's effectively how all the databases do it. They have a way of marking the sort of the time that row was created, the time that row was expired, and then they filter through some of these duplicate rows to make sure that you get a consistent view of the database every time you run a query. And in fact, there's no way in Postgres to get an inconsistent view. There's no dirty read is not even supported in Postgres. If you ask for dirty read, you'll get a read committed. There's just no way to even see inconsistent results. What happened in the older pre-MVCC systems, they had to have a way of showing dirty data because a lot of reports just couldn't finish. But because of the way Postgres works, there's no value really to giving you stale data. We have both rows available anyway, so we just always will give you a consistent view. Even if you ask for a dirty read, we will not give it to you.
That's right. Yeah, that's really cool. And so, it's really interesting when you mentioned like the idea of a snapshot. And I'm just wondering, like, kind of how does Postgres or MVCC, because obviously one of the things you did mention in your talk, and I definitely put that in the show notes, the MVCC Unmasked talk you give, kind of explaining the very scary looking if conditional to work out visibility. It is very scary, but it works, and I think it's very interesting. You've got like a little comment in there saying, someone's mentioned, they're saying, yeah, this does work. I've tested it, and if you think it doesn't work, you're wrong.
Yeah, that is kind of a hilarious one. That's actually slide 12, and I actually know Mike Olson, so it's kind of funny to read a comment from his much younger years. And he's really, I think it captures a lot of the sort of angst that we all feel when we do look at the code in this way. That again, one of the goals here, like singing the national anthem, is just to make it, just to get up and make it look effortless, right? But it rarely is. And when we talk about actually working in the internals of Postgres and tracking these snapshots and tracking row versions and stamping row versions and so forth, it gets a little sort of mind bending, because you think of when you look at an object on a table, you sort of say, well, either the object's on the table or it isn't on the table, right? I mean, I'm looking at my glasses. My glasses are sitting on the table. No matter who comes in the room, everyone will see those glasses on the table, right? I can bring 1 million people in, and they're all going to look and see the glasses sitting there. What happens with MVC MVCC is slightly different. So because what happens is things are moving around on the table as people are entering the room, and depending on when you entered the room, you may see an object in a different position at the same time that somebody else who's also in the room will not see it in that position. So you may have two people both viewing a desk. One will see the glass in one position, and the other will either not see the glass at all, or will see the glass in a different position, even though they're both in the table at the same time. And the real test and the real difference is the time that they entered the room, because you're basically guaranteeing that when you start a query, or effectively when you start a transaction, you're guaranteeing that you will see the table unchanged at the time you enter the room, even if you don't get to the glasses until 20 minutes later, right? The glasses may not be there anymore for somebody who's newly entering the room, but for somebody who's been in the room for 20 minutes, they appear there. And that is very odd. You start to get into, it almost sounds like an Einstein relativity experiment at a certain point, because you're kind of seeing reality is not reality. Reality is changing all the time, and your job as a database administrator is to give everyone a static reality. Because if you start to give them realities that change, they can't do their jobs. They cannot, they cannot find out how much money was in the bank. They cannot reconcile reports, and you go back to having to do everything, single user mode if you want accurate answers, and that really just is very limiting for any large organization.
So with some of the snapshot stuff, you've mentioned kind of that there are different ways of kind of making this snapshot, and it all depends on like your transaction isolation level. I'm just wondering kind of what are the different ways of doing it based on like transaction or query, and what are like kind of merits?
So, as I said before, most people don't really think about this. They just run their queries, and they know they get consistent results, and they just go away, right? But there is a sense that you can leverage some of this knowledge to actually make the database more useful. So let's think of the simple case. So the simple case is you run a select query outside of a transaction. Postgres has two modes. One, you can run a query alone outside in its own transaction, effectively an implied transaction, or you can start a transaction block with begin work, and then run a whole bunch of commands together. So let's start the first one. The first one is you run a command sort of in its own implied transaction. The way that works is when the query starts, it takes a snapshot of the database, and there is a slide here. I think it's slide number 10, which does sort of explain what types of things are recorded when a snapshot is taken by a query, and that snapshot never changes throughout the entire lifetime of that select statement. And obviously, when the select statement ends, the transaction ends, it commits, whatever. And then the next statement, the next select, would effectively take a new snapshot. So again, if you're not using transaction blocks, every select you issue is going to get a new snapshot. And what that means is that if a row is added between the first select and the second select, the first select is not going to see it. We've already talked about the fact that MVCC gives you a consistent snapshot. So therefore, you never see new rows as the query is running. Okay, but the second select will see the new row. Okay, now if you use a transaction block, believe it or not, that behaves the exact same way. So if you say begin work and you issue a select, okay, that select is not going to see a new row that gets generated while the select is running, but the second select effectively is going to see the new row that was added while the first select was running. Okay, and then similar to the third select and so forth, or updates the same thing, deletes the same thing. They're all follow the same snapshot rules. Okay, so that's something people kind of are surprised a little bit about, that while you don't see new rows or new changes during a select, by default in Postgres, you're going to see new rows in the next select or the next update or delete. So each new command by default will take what we call a new snapshot. And that new snapshot will control what rows it can see, and by default, those rules will allow it to see changes, any changes that were committed prior to that snapshot being taken. Now, I said there's a way of leveraging this. If you put your transactions in a transaction block, again with begin work and commit work, and you issue a statement at the beginning, right after the begin work, to set the transaction isolation level, either to repeatable read or to serializable, what will happen is that you will not get a new snapshot between the first select and the second select, and between the second select and the third select. Effectively, when the first command is issued after the set transaction isolation level for repeatable read or serializable, a snapshot will be taken, and the same snapshot will be used for every single query in that transaction block until you either commit it or roll it back. And the reason that's very useful is if you're running a report, you can effectively run multiple queries in that transaction block and guarantee that all of those statements see the exact same data during the entire length of that transaction. That transaction block could run for hours. It could be a huge report, but you're guaranteed that you will not see any data, any new data. You will not lose any data that's deleted that happens during that transaction block. So the command is set transaction isolation level. There is a manual page on it. There is Postgres documentation that covers it in detail. And a lot of people find that very, very useful because it does allow you to kind of control when you're getting a new visibility of the database. By default, as I said, Postgres is going to give you new visibility of the database for every new command, but set transaction isolation level allows you to change that. In addition, I've talked a lot about select queries, but if you use serializable mode, isolation level, then effectively Postgres will allow you to do not only selects but updates and deletes. And if anyone changes the database while you're making changes to the database yourself, it'll actually abort your transaction. So it will prevent you from perhaps seeing data that got changed by somebody else, and you go to change it, and it's like, oh, that could not be done in a serializable fashion, so I'll abort this transaction. And it actually makes it very easy for application developers to not have to worry as much about, for example, select for update. They can actually run in serializable mode and be sure that all of their queries, even if they haven't done the proper locking from one select to the next or from a select to an update or delete, they can be sure that they're actually seeing a serialized view of the database. And if there's some anomaly that would cause a non-serialized view, one of the transactions will be aborted.
That's really interesting, really interesting. And so with MVCC then, like, are there any cleanup considerations that have to be, because obviously you're saying that we've got all these snapshots and we've got all these different points in time. Like, how do we go about kind of cleaning up or dealing with that kind of case?
Yeah, and I would say, although a lot of the databases now implement MVCC, I think that the ways that individual systems handle the cleanup is really probably the distinguishing mark between all of them. For example, I think the reason DB2 only has partial MVCC support is that the length of time at which they will save old versions is fairly limited, and that might have changed since I wrote this presentation, but I haven't been informed that it's been changed. Somebody, you give a talk at a conference and Mr. DB2 expert shows up and can answer almost every question you have about how DB2 does stuff. So I have to wait for that next person to come along to make sure these are all accurate information. But the real bugaboo, the real problem with all of these systems is the threat of old versions clogging up the system. And the threat would seem to be pretty pretty innocuous. But when you think of long-running reports, which may create very long-running snapshots, particularly if they're using repeatable read or serializable isolation level, you can't clean up some of these rows that these sessions may potentially want to see. So if you have a financial report that runs for 8 hours, you're limited in how much cleanup you can do in the database that they're connected to, because you don't know what query is coming down the pike that might need a copy of a row that was valid 7 hours ago or 9 hours ago. Okay, and that's really where you get caught is where do you store these old rows so they don't sit around too long and take up too much storage space? Do you place some kind of hard limit on how long they can stay around? And where do you keep them? Do you keep them in the table itself? Do you keep them in some type of area that's separate from the table that has to be cleaned up separately, that lookups have to do separately? And that gets confusing. And I think all the systems kind of do that differently. Is where to keep these rows, how long to keep them, and how to clean them up.
So how does Postgres do this then?
So the way Postgres does it is I would argue one of the simplest ways, and it does allow for some really kind of clean implementation ideas and some optimizations that we may or may not get into in this talk. But effectively, the way Postgres does it, if you update a row, for example, which is probably the canonical case of MVCC, we just leave the old row where it is. We just create a new row. So, if we go back to the example we talked about earlier, row number 7, we currently have one version of row number 7. Somebody comes along and wants to update row number 7. We're just going to leave the old row number 7 unchanged as it is, and we're going to create a new version of row 7 somewhere else in the table. Okay, and the MVCC rules automatically will filter out the old or the new row. So nobody will see two versions of the row. Every transaction will either see the old version of the row or the new version of the row, because each row has enough information that allows us to filter it properly, given the MVCC rules of the snapshot that's being taken by the individual transaction. So the only cleanup really for Postgres is we've left the old row in place, we've created a new row, and then at some time later we need to come around and remove the old version of row number 7, assuming that the new version of row number 7 is part of a committed transaction and not an aborted one, and assuming that no old transaction still needs to see the old version of row number 7, we can then blank out that space and make it available for reuse by someone else.
So when does this actually occur then? When do we decide then, okay, now I need to clean this up, and what actually actions on it?
So there are actually two ways that a row can be cleaned up. And fortunately, both ways are invisible to the user. So users never see this. They don't have to do anything to make it happen. Administrators also don't have to do anything to make it happen. So, in a way, it is sort of set and forget. The two ways you can do a cleanup is if Postgres is trying to add a row to a specific page. Postgres has 8K pages stored on disk. And if a page is fairly full, I think it's 90% full, I think is the threshold. If a page is fairly full and we'd like to put a row on that page, we can do sort of a single page cleanup. It's called a hot cleanup. I don't know how to explain that, but effectively what we can do is when we're on that page, we can say, we'd like to put a row in this page. The page is is on the full side. It's over 90%, let's say, full. So what we're going to do is we're going to look at the rows on this page, and we're going to look at the current transaction numbers that are running, and we're just going to remove any rows on this page that happen to be expired and no one can see them. So the beauty of that system is that effectively, as you're trying to do the insert or the update, you're like, hey, this page is looking kind of full. Let me just look through these rows. Oh, look, I've got 3 rows here that are old, are expired. They're no longer visible to any transactions. I'm just going to reorder all the rows on this page. Now, oh, hey, look, now I have, 1,500 bytes free that I didn't have before, and I'm going to put the row there. In fact, this happens even during select queries. So it's not even necessary during an update. If a select is looking for a page, it potentially can kind of clean up that page and kind of get rid of the old rows as it's kind of going through. So it's so low maintenance that effectively nobody even notices it. It doesn't really show up as something that you would notice a query being slower. Postgres is reading through these rows anyway. If you're doing a sequential scan on a table, for example, it's reading the row anyway. It has to look at this transaction IDs to determine if that row is visible or not. So why would we not clean it up, right? And that is a tremendously useful feature because you can basically clean up stuff real quickly. Now, the problem, unfortunately, is that there are often indexes pointing to that data page, to that row that's been expired. And the cleaning up of the index entries would be very expensive and something we really cannot do during a cleanup of a select, for example. While we're running a select, we don't want to be running around the index doing cleanups. So we have a heavier weight process called vacuum, which is automatically triggered based on how much free space is potentially in a page, and it might take several seconds or even a minute for this vacuum process to run. And it's kicked off occasionally by a process called auto vacuum, which is constantly monitoring the statistics of the table. It's looking at how many deletes have happened in the table, how many updates have happened in the table, and it will basically run and it will scan through the table. It'll do a little more aggressive reorganizing of some of the table contents, and it'll also remove any of the index entries that point to these old rows. So the nice thing is that all that happens invisibly. The users don't notice it. The vacuum process is fairly lightweight. It doesn't lock anything. It does consume some I/O, and it's obviously going through the indexes. But the large majority of cases, these are very lightweight operations, and something that really doesn't impact the system at all. And it allows Postgres to run, virtually forever with almost no maintenance, even though we're accumulating old rows and deleting them occasionally.
So you mentioned there kind of like some of the internals of how Postgres actually stores these rows, and you said like pages. I'm just wondering, could you maybe like go into more depth what you mean by a page and an 8K page and how that kind of works?
Yes, that whole architecture of storing things in pages and the sort of layout really came from the Berkeley folks that we sort of inherited the code from in 1996. The idea is that instead of storing your data as a continuous stream, which is probably the way you would normally think of doing it, like you would just have 100 rows and they'll all be just right next to each other, right? The idea of Postgres, the idea of most of the relational systems is that the table or the index are broken up into segments. And the segments have certain housekeeping fields surrounding them, and because they're broken up into segments, you can basically more easily work with the data. So the Postgres has by default an 8K segment or 8K page. So you may have a table that takes let's say 64 kilobytes of storage, but internally that's made up of 8K pages. Okay, so similarly, if it's a 32K table, it's going to be 4 8K pages, and each page has a header, it has a footer on it, it has item pointers which exist at the beginning of the page, which are pointed to by the index, and then it has the majority of the page is the data itself, effectively individual rows which are stored sort of sequentially within the page. But because of the way they're laid out and because of the page structure, we can move the rows around within the page to compact it without affecting, for example, the index or without affecting concurrent access. So that allows us to kind of restructure the page, particularly as we're doing cleanups with single page vacuums or the more holistic vacuum command with auto vacuum, where we're moving stuff around. We can move stuff around within the 8K page without really affecting concurrent access, and we can really touch an individual 8K page without affecting access to other 8K pages. So we could potentially have cleanups happening on all 8K pages at the same time. So if you have a table with 5 AK pages, you potentially could be doing cleanups on all 5 simultaneously. That would not be possible, obviously, if you store them all sequentially. You really kind of need a structure around each page and the ability to pull certain parts of the table into main memory without having to bring the whole table into main memory, for example. And this infrastructure around the AK page and so forth allows for the cleanup to happen more efficiently.
That is very, very cool. And then, so you've mentioned like vacuum, auto vac, and you've mentioned the single page like cleanup. There's also another one called vacuum full. I'm just wondering, like, what that actually does then, that vacuum or the single page vacuum or single page cleanup, does.
Yeah, vacuum full is more of a. It really came in as an artifact of the original Berkeley implementation. The original Berkeley implementation did not have this very lightweight type of vacuum operation. Effectively, you had to lock the table to do major cleanups, like we're doing now, which it hasn't been true for decades. But you can think of a vacuum full as basically a compressed process. It will basically take the table and completely rewrite the table, removing all free space so that it's completely compacted. But unfortunately, to do that, you have to lock the table. So it's really not an operation you see people doing very often anymore. I mean, they haven't done it for decades. In the old days, again, in the law firm example, you'd run vacuum full maybe on the weekend when nobody was in the system, and you'd get back a couple megabytes of space, and you'd be all excited, right? I mean, it was sort of a maintenance operation that you'd run. Just to clean things up. However, if you look at modern Postgres, vacuum full is really only used in a case where you've massively deleted huge amounts of data from the table, and you never are going to reuse that space. And in addition, the data that's been cleared out is not at the end of the table, but maybe in the middle or at the beginning. And vacuum alone can't shrink the table down, and you basically have to do some kind of outage for that table. And basically, let's suppose you've got a table that used to have 100 million rows in it, and now it has 100 rows, right? You can vacuum that all you want. Actually, that case might work because vacuum alone can remove trailing pages. So if you've got a lot of free space at the end of your table, vacuum itself can shrink that down. But if you've got like one sort of sticky row at the end of the table, and you've got a huge amount of free space at the beginning, and you want to reclaim that space from the file system, the only way to do that is vacuum full. So that's the one case where you would have to take an outage for that individual table and lock it and do the vacuum full. And then obviously once it's done, all the indexes would be rebuilt, the table would be rebuilt, and then once that completes, everyone could go back in and continue their work. You don't see it used very much. We also have a reindex command. Again, that doesn't get used very much. But there are anomalous cases where massive data changes sometimes do require some kind of outage for individual objects. Not for the whole database, but again, for those individual objects, for you to sort of restructure the way they're stored. And that's what vacuum full does, and effectively reindex does the same, but just for indexes instead of doing it for the entire table and indexes together.
That's cool. And actually, I don't know if you've noticed the project PG Compact that kind of goes about so in a vacuum full light essentially that tried to mitigate the exclusive locks.
Yeah, that's a really interesting project. We used to have another one called PG Repack. So there's actually 2 projects that have kind of tried to do this. They're very interesting. So remember I talked about the fact that vacuum can trim off empty pages if the empty pages are on the end of the table, right? So if the empty pages are at the end, when vacuum runs, it can use what we call F-truncate, which is supported by all modern operating systems, which can basically say, this table currently is 100 megs, but I really only want 80 megs of it. So take the last 20 megs and just trim it off, right? But we can only do that if those 20 megs are completely empty pages. And of course, Postgres knows if those pages are empty, and Vacuum automatically will trim those off. But as I said before, if you've got that one stubborn row, which is out at, byte 98 megs, you can't trim off beyond that one row because you need that row. And Postgres, by definition, will not move that row on its own. What pgrepack and pgcompact attempt to do is to sort of look through the table if it has a lot of free space and look for some of these sort of outlier rows which are sitting at the end of the table and try to transparently migrate those to earlier parts in the table so the truncation can happen more seamlessly. So it's basically trying to move some of the stuff at the end of the row toward the beginning of the table where there's more free space and allowing Vacuum to then truncate off more of the trailing edge of the table. So that's what those attempt to do. It is dangerous. It's not dangerous by definition, but you don't want to get that wrong because obviously you're trying to do this while people are accessing the table at the same time. So you have to follow MVCC rules. You have to make sure that your move you don't trim it too quickly because you've got to move the row. Maybe just update the row, and change nothing. Maybe you just update the row. You don't change anything, but maybe it has new transaction ID, so you've got to wait for the old transaction ID to go. And sequential scans on the table, maybe reading that row, so you've got to make sure they don't see the row twice. So the only complexity there is that those tools really have to understand the Postgres internals very well to do this safely. And it is tricky. I guess at some point we could try implementing this inside of Postgres. I'd say the jury's still out on that. We do have a lot of customers I know for Enterprise DB, who's my employer, who are really excited about this kind of capability. But at the same time, we want the database to be 100% reliable, and it takes a lot of research to do this right. And I guess if it becomes much more popular, we're going to have to try and find a way of doing this in core Postgres, where we have full knowledge of everything that's happening in the system and all the visibility rules and everything. But I say the jury's still out on that one. It's a very interesting approach, and I understand what they're trying to do. It's so tied to the internals of Postgres that it can be a little scary sometimes to sort of move stuff around like that. But yeah, I think there's even more than two attempts of sort of trying to reshuffle rows around to make the trimming of Vacuum more efficient. That's really what they're trying to do.
Yeah, because I was going to ask actually if this is something that Postgres internals or core was kind of thinking about maybe implementing. But like you say, it's got the problems and any issues have got to be weeded out, before it goes into something like the core.
Yeah, we do have a to-do list which kind of alludes to that a little bit. There's an item that talks about, for example, one of the ideas would be when you're inserting into a table that has a lot of free space at the beginning, let's say, should we be favoring earlier parts of the table? And the idea would be that if you favor earlier parts of the table for free space, then over time, the later parts of the table would be more easily trimmed, right? Would be expired and therefore allow the table to trim. But I would almost say we really haven't thought of Postgres at this level yet. It's something that's kind of cool, but it's still really an edge case behavior that people are doing massive deletes on their table, but they've got like a lot of stuff at the end, which you don't see a whole lot. So I don't know. I think we have a to-do list that we've had on there for a long time to sort of try and be a little more strategic about trying to help the trim operation. And right now, the to-do item really talks about adding new rows, but the idea of actually having vacuum move rows from the end of the table maybe earlier is something that I definitely think we could take on something like this. This is not a static area. We continue to make improvements. In fact, we're working on some stuff for Postgres 10, which would make the cleanup of rows even more aggressive. And I've seen some benchmarks which write-heavy benchmarks would actually increase actually double the performance of Postgres by allowing for more efficient cleanup of multiple versions of these rows, because right now you can't do single page cleanups if anyone changes an index entry, because the index has to point to the same chain of rows, and if anyone changes an indexed column, you can't have the chain no longer has a unified index structure anymore because the indexed values change, so you're not getting the advantage of these single page cleanups sometimes with actually the advantage of actually having one index entry point to a chain of rows, which is another thing I didn't even talk about. But as I said, when you do an update and you create a new copy of a row, do you need to create a new index entry? And if none of the index columns have changed, you don't. You can actually create a chain of versions of a row, which all have to exist on the same 8K page, but actually improve performance dramatically, and we're working to even improve that, so you can have changed index columns and still have a chain of rows within a single page. So I would say we're still improving this area, and there's still quite a bit that can be done, I think, to make it faster. Some of the other database engines have taken different approaches to this, and I think it adds a lot of complexity to the system, and it limits some of the optimizations that they can make. So it's again, no part of Postgres really sits idle. We have, again, some people working on the repack or the reorg or the compact. In fact, I think we have a reorg and a repack and a compact. We have a bunch of things that have tried to do this, and I think eventually it would be an area that we would get into. But I think there's even bigger parts that we're kind of chewing on for Postgres 10 that I'm excited to see. I think it would be another real boost to that.
Very, very cool. And finally, again, thank you, Bruce. I really appreciate you taking the time. Just something you did mention, and it kind of goes around with the pages, is the idea of like a fill factor and how you can tweak that to manage, performance and size of your database. I'm just wondering, maybe you could just give a brief overview of what the fill factor is and how that helps.
Yeah, that's really a great example. A lot of people assume that the best way to get performance of their database is to 100% fill all of their tables, and they're probably also thinking 100% of their indexes. So they would think that the best case would be 100% table fill, put as many rows in an 8K page as you can, and 100% fill factor of your indexes, which means put as many index entries in an 8K page as possible. But the fact is that that's not optimal for a couple reasons. For indexes, it's pretty clear. What happens when you 100% fill an index is that it's the first time you need to add a row to a particular index page, you have to split it. Okay? So if you 100% fill factor your indexes, then the very first insert that has to put a row in that index is not going to find a room in that page. Is going to have to split that page into effectively two 50% filled pages. Okay, and that's going to happen for every fill page in that index until they're all split. Now, if you have a read-only database where you're not doing any inserts, that might be fine. Okay, but by default, Postgres knows for a read-write database that's not good. So Postgres, when it creates indexes, I think it has a 70% fill factor. And that's because we know that people don't want to be page splitting the minute they go to do an insert. And frankly, two 50% filled pages is worse than one 70% filled page. right? Because obviously 50% filled of 2 pages is, you're really under a 70% fill factor at that point. So indexes by default, pretty much all the vendors don't fulfill their pages unless it's a read-only database, because they know that as soon as you have to put an entry on a page, you're going to split. Now, with Postgres, it's a little different because we can always expand the table, right? Because remember, index pages, if you have an index page for, A to F, you got to put it there. That's the only page that contains A to F. You've got to put the entry in that page, and the only way you can do that is to split the page and then, have A to C and D to F or whatever. Okay, so when you're doing index inserts, you really don't have a choice of where to put the row. It's got to go where the index tells you to go. That's not really true with tables. Again, you can say, okay, every insert, we create a new page on the end of the table, we put it there, right? So you had seen that would work fine. And in fact, Postgres by default uses 100% fill factor for tables. The problem, though, is regarding this chaining, these hot updates, which I kind of talked about when I talked about single page vacuum. When you're going to update an individual row and you don't want to create new index entries, the only way you can do that is if you put the new row on the same 8K page as the old row. And if the 8K page has no free space, you can't put it on there because it's full, right? So either you have to delete some data, which you can't do at the time you're doing the update, or you have to go and create a new update somewhere else, and then you have to create a new index entry, and now all of a sudden you can't do this type of single page cleanups as efficiently as you could do if the page had some free space on it. So you would kind of think that, well, maybe I should create my tables not with 100% full factor, and a lot of people who are doing heavy update loads will do that. However, if you don't do that, what effectively happens is that rows that get a lot of updates end up migrating to the end of the table, and they also end up being placed on pages that are virtually empty. So the good news is that what happens in a database that has 100% fill factor for tables, over time your updated rows will migrate to empty pages because they will not fit on the full pages, and by definition those pages that they're put on have a sufficient amount of free space, and therefore we will be able to do the type of hot updates that are very easily cleaned up on those sort of outlying pages. So what effectively happens when we implemented hot, I guess 12 or 10 years ago, and we sort of thought about how this was going to behave, and we realized that effectively what happens is that the updated rows end up migrating to the pages that have a lot of free space, and the rows that aren't changed or aren't updated effectively probably just remain in that 100% full factor page and either never change or rarely change. Maybe they get deleted and then some free space frees up. But if you think of the way a table kind of looks on disk, you probably have maybe 90% of your rows are pretty static and don't change a lot. And probably you have those 10% of customers or 10% of products that are just changing all the time. And those end up being on pages that are primarily have sufficient free space to allow you to do those hot updates. And those probably are also the pages that end up being in the cache. So we've found that even people who don't change the fill factor for their tables end up they probably do not get good performance initially when they load their database and they start doing updates, but within a short period of time those high update rows have migrated to pages that have sufficient free space, and the system starts to work a lot more smoothly. The cleanup starts to happen a lot more efficiently, and they get very, very good performance at that point going forward.
That's really, really interesting. And again, thank you so much, Bruce, for taking the time out to discuss all these things. I think as I said, like at the beginning, it's so interesting learning more of the internals of a database and that things aren't just magic, that there is a reason and a way that they work. And sometimes it's really good to kind of at least understand kind of at a high level, and then obviously sometimes be geeky and want to learn at a low level why these things happen. But yeah, as I say, I really appreciate you taking the time to come on the show.
Yeah, it's really interesting to me because there's just so much thought that has gone into this, and obviously because Postgres is developed in an open source manner, you have thousands of people who are always sort of putting their 2 cents in or giving their ideas about how a certain thing should be implemented or how a certain thing will behave under certain workloads, and you're always learning from them. You're always saying, "Oh, gee, I didn't thought, gee, that would." Yeah, I guess that would be a problem, or oh, that would work really well if we did it this other way. So you really get access to some really, really smart people, and people who are thinking deeply about these type of behaviors and different ways of implementing things. And when you finally are done and you actually ship a final version, there are so many people's ideas sort of intertwined in the actual implementation that goes out, that really one person doesn't do it. It's really an amalgam of many people who have all given small ideas that kind of built on other ideas that were earlier. It happens within a year of when a feature gets developed and actually pushed out. But so many people make so many ideas, and each person advances it just that small amount, that when you get to the final feature that gets shipped out, it has an incredible amount of polish on it, and there's sort of an incredible amount of thought that goes into how this is going to behave in so many different workloads, that it's surprising how really kind of spot on you end up being, because at the time you're going through it, it feels as though there's dozens of roadblocks where this is not going to work well, and you basically you overcome each one with with sort of intense discussion within the groups. But when you finally get to the end and nobody has any improvements to make, and nobody has any ideas that would make it better, you're like, okay, we're done, let's go, and it gets shipped out and it goes into production, and you find that we really did hit everything. We're not perfect, but it's amazing how complicated some of this stuff is, and it's amazing how close the project gets to really hitting almost every area that needs to be sort of polished to make it function well in production environments.
Yeah, absolutely. And like you say, this is the beauty of open source, where everyone's working together for a common goal. But yeah, again, thank you so much again, Bruce, for taking the time to come on the show. And audience, I think this is a good place to wrap up. Another great episode. And I'll speak to you again next week. Goodbye.
You've been listening to 3 Devs and a Maybe. You can contact us at contact@3devsandamaybe.com. Or follow us on Twitter at 3 Devs and a Maybe.